Hello again. Very warm welcome for you who attend in person and who attend online. This session is going to be about the machine learning application of AI and machine learning. So I was thinking that it is good to say, if we understand in a simple way, we won't be afraid of machine learning and AI. So we tried to talk about machine learning and AI in a very simple way. My name is Ramiz. I am a PhD candidate in Center for Water System, University of Exeter, and I am currently working on a project which is application of machine learning models for environmental aspects. And I am also contributing to the R&D team of Data Techniques Corporation in Manchester. Milad?
Yeah, thank you. Good morning. No. Afternoon. I'm Milad, and I'm doing my postdoc in Center for Water Systems at University of Exeter, and I'm working on knowledge transfer partnership project between University of Exeter and Data Techniques Corporation, company based in Manchester. The focus of my project is to predict the failures in water pipelines and develop some sort of digital twins to predict the remaining lifetime of the assets, like pipes, valves, pumps, and anything in the water distribution systems. And in my project, and also Ramiz's project, we are broadly using AI and machine learning tools in real-world projects.
Yeah, very well. So, as an overview of what we're going to present today is about the introduction about the AI and machine learning. Then we're going to talk about a bit about data science basics and machine learning. So there are some terms that you will hear it, and it is about the general discussion about what it is. And then we're going to talk about the machine learning models, performance evaluation of the models, and so how we're going to test them, if they're accurate or not. And later on, we will have a very good discussion, I'm sure. So,
yeah, when we talk about data science, we have different areas. For example, if you want to have a machine learning model, we have to combine knowledge from computer science and maths and statistics. Or if we want to talk about data analysis, it's about domain expertise, knowledge expertise, and also maths and statistics. And for example, if you want to develop a software, a traditional software, we have to have both disciplines from computer science and domain expertise, business expertise. But data science is about all these three realms: computer science, domain expertise, and maths and statistics.
If you ask, where is data science today? Data science is everywhere. So you will see science, humanities, and policy, art, engineering, society, everywhere. So when we're talking about data science, when we're dealing with data, they are everywhere. So if you are hearing some podcasts, if you're reading a paper, they're always a sign of data science inside of it. So, and what about if I put some categories in it? The main thing of application of machine learning and artificial intelligence is in these categories, which when I was preparing this presentation. The first thing: virtual assistant, social media, transportation, financial services, healthcare, online shopping. But how?
For example, in healthcare, now we have applications, softwares, which are able to analyze and process the radiography images to understand and indicate what is the disease of a patient. Or we have some sort of robots where they're able to do the stitching automatically without any help from a GP.
Of course, we're going to have some kind of automatic robots for surgeries in coming years, for sure. So about this transportation, the known guy, which I'm not going to say his name if you want to say it.
Elon Musk.
Yeah. All right. The known guy was famous for the self-driving vehicles. Also, I remember one of the first things which I read in the BBC News was about automatic park in vehicles. So in some cases, we are applying some kind of machine learning. They are learning, and then they are processing. So
So they learn how to drive,
Yeah.
and then they drive.
Correct, exactly. So it is the application in transportation.
And also, yeah, in finance, we have some banks who use some sort of applications to detect fraud in bank transactions. You want to go?
And social media, which you all know that it's always obvious. And that when you go in and it's Facebook, when you want to tag someone, and it gives you some suggestions, which maybe it is the person. So it is image recognition, and also then we come to the YouTube, Facebook, Twitter, X, and LinkedIn, Instagram. When you're using them, they're coming out of the suggestions and recommendations. Oh yes, this is a good point. I was trying to buy Milad a Manchester United jersey last year for his birthday. And when I click on this jersey, there were so many suggestions, like Manchester United mugs, I don't know, red t-shirts, devils. So they are all coming from the application of machine learning, or let's say AI. So it is learning from different items, and it is gathering the similar items, and it is showing you the suggestions that you can put on. It is another application of that. So you can see it in Amazon, Alibaba, eBay.
And yeah, now we have virtual assistants like Siri, Alexa, like Google Meet, and they can understand what we are talking about, and they can find the correct answer. They can answer us, very similar to a colleague, to a friend, and an assistant, a real assistant.
So it is as simple as saying, hey Siri. And about the environment.
Yeah, this is the project we have developed in the last 2 years. And yeah, we have developed a machine learning model which is able to get data from the sensors which are deployed on the real water pipeline network, and pushes the data into a machine learning model which is able to predict the health care of the pipes. It means that whether a pipe is going to be deteriorated, degraded or not. And having such a system, the operators and asset managers in the water distribution network are able to predict the failures and replace the pipes before they fail. They really fail. Yeah,
the main goal of this model was to have the pipe condition assessment and also say what is the remaining lifetime of the asset in the water distribution network. So, about the history of data science. You know that maths and statistics were there before computational age, or let's say computer time. So, and the ideas of machine learning and data science, let's say, was there before the computers. And we need the hardware to, develop more ideas and use these algorithms. So later on, with the Turing and the other famous guys, the computer age begins. Later on, we are talking about genetic algorithms and optimization, which Babak was the expert. And then we come to the data mining time, which is now we have data, so how we process it, how we could, develop some models on this data. And today, we're dealing with big data. So in each field, we have data, and we need to process it. We need to understand data better and have our algorithms which learn better from that data. So, about the future of data science. You could tell us that what is going to be the future of data science? And we will discuss it.
How the data science is going to change our life.
Yeah.
How machine learning is going to change our life.
Exactly.
Any idea?
Any ideas about how it is going to change our lives?
What's the future of data science in our life?
No?
How far in the future?
Very good.
2 to 5 years.
Yeah, 2 to 5 years, or maybe up to 10 years.
Not in 100 years.
Sorry?
Remove a lot of entry-level jobs.
Yeah, great idea.
Good idea. Let's discuss this one, yes.
Great idea and a great concern.
Could be.
For all of us.
So, yeah, we'll discuss it in the end of this presentation. So, when we're talking about data science, there are some terms that you may hear in some of the podcasts and papers, and you want to understand about these terms. We're going to briefly discuss this. So, mainly about data.
What's data?
Oh, good. Very good question. Data is collection of facts and or some kind of measurements, observations, numbers, strings, booleans, and data could be inside of some kind of rows and columns. Rows are records, observations, and also columns are features and variables. As you can see, this is a sort of data. If I gather our name, don't look at our age. And we have some values inside of it, columns and rows. So this is some kind of data. And about the dependent and independent variables. So we have, when you hear about dependent and independent, it is a mathematical thing. So dependent variable Y is something that we want to find or we want to predict. But dependent variable, independent variable is something as knowledge it's giving to us that we're going to use it and find the dependent variable, which is depend on the X, like a mathematical function, which is Y is equal to Fx. So we're trying to find Y by having the knowledge of X, mainly.
Yeah, and when we talk about data, outliers and missing data are quite common. We hear about outliers and missing data. The easiest way to find outliers is to visualize the data. For example, here in this figure, you can see we have two red dots, which are quite far from the other parts of the data set. It means that these are two outliers. It's quite common that we have outliers in the data when we have errors in experiments or some errors in the devices that do the measurements or things like that. So what we have to do with these sort of outliers? Do you have any idea?
Remove them.
No, it's too radical.
Okay.
Yeah.
So what do you suggest?
Yeah, if, for example, if you have numerical values, an idea would be to replace them with mean of the data, median of the data, random sample values, or the regression values.
Yeah, okay.
Yeah. Or if they are categorical values, we can replace them with mode of the data or with the KNN prediction values.
If you don't know about regression and KNN, we'll talk about it later. So don't worry.
Don't worry about that.
So, wait, excuse me, isn't there a third solution?
There are many solutions. There are many other solutions.
It is for general discussion, so we can't have it all of them here.
Because
What is your
sometimes
suggestion?
outlier, I mean, what are detected as outlier are actual data.
Yeah, yeah,
And,
yeah.
You know, it could be confounded for an outlier, but actually they are like important pieces of information, so removing them would be
Yes.
So radical.
problematic.
Yeah, this is my idea to remove them. So we have so many solutions to go. Yes, and how machine learning learns. It is quite nice that to define how a machine learning learns. Just like a baby. So it is going to learn just like a baby. So how a baby learns. Would you be my father for next 30 minutes? So I'm going to define this one. So
Should I teach you something?
let's say I'm the son, I'm the baby. Now I want to learn something about the fruits. We have a bowl of fruits in our house, and Milad is going to teach me as my father what is what. So I have apple, and I look at the orange, and I said, it is a round shape. So I memorize it in the first learning phase that there's a round shape, so it could be apple and orange. So I memorize the shape. Then I look at the cucumbers and bananas. I said that yes, it's a cylindrical shape, it's tube-like. So I memorize the shape again. I go to the other phase, other learning phase. So if the shape is round and if it is red, it is apple. I memorized it. If it is round and if the color is orange, the fruit is orange. But I learn about the fruits with Milad, who is my father. And later, my knowledge is gathered in the data, just like a data in my mind, from the bowl of fruits which we have in our house. So as you see, there's some shape which I remember, color, and then I labeled them as a fruit names. So this is exactly what a machine learning does. So let's test it. Later, you asked us to come for a coffee to your house. And you have another bowl of fruits on the table. I never saw the fruits because it was in your house. And Milad was going to test me to see that I'm not dumb. So
You're my clever
so
son.
the first thing, he gave me a fruit and said that, I looked at it and I said, okay, it's round and it is red. So I'm going to think about the observations I had before. And later, I would think, okay, I saw something like that before. And then I said, it's an apple. Wrong. So I'm not done. So it is the case that how it learns, how we test it. And now,
Ramiz, let's make it serious.
okay,
Okay, so if you have data like fruits, apples and oranges, every data has their features like shape and color of fruits, and also they have some sort of labels, which means that whether it is an orange or an apple, and this is the structure of the data that we have. We have to predict the label through the features.
exactly. So let's come to the types of learning in machine learning, which is something we have to discuss. Broadly, there are unsupervised and supervised learning. So let's get back 1 week before Milad taught me about the fruits. 1 week before, the bowl was there with the fruits. And I was a curious child to look for the fruits. The first thing, I didn't know about the name of the fruits. I would try to categorize them somehow. I said, all right, these aren't similar. I put them aside. Without knowing the name, without knowing anything about that fruit, I was able to just put them in some clusters. I put the oranges in the right side, put the apples in the right and the left side. So I put the fruits which are similar to each other in a side. So it is something that unsupervised learning, which Milad was not there, and I don't have any guidance. So I have the inputs, which are the fruits. I am the algorithm, which I learned about it. I tried to learn. I labeled them by my own. And I label the fruits in some clusters. So it is something we call as unsupervised. But a week after, Milad trained me, let me learn about what is what. So I know the labels. In this case, I have the fruits. I have the, let's say, features of what is fruit like. And I know the labels. In this case, I learned what is what by having the label, having the guidance of Milad. And later we moved to Lene's house, and we had a new fruit, which is similar. And then I knew about my before, and I could predict what is, or I can say, what is that fruit without saying it. So if we go to the modeling.
Yeah, how does a machine learning model works? Simply, very simple. If you have a whole bunch of data sets, first, we divide the whole data set into two parts. A majority of the data is going to be used for training the model. Typically, 70%, 80% of the data is going to be used for training the model. And the remaining 20%, 30% of the data is going to be used for testing the model and evaluating the performance of the model.
Like you did in Lene's house.
Yeah.
Yeah. Good. And do you want to talk about the overfitting?
Yeah. And maybe you have heard about overfit model or underfitted models. When we talk about the overfitted models, it means that the model is so complex, it's very complex, in a way that the model works very well, very accurate on the train set data. It's like the model memorizes the data in train set data. And it is not very accurate, that accurate in a reasonable level to predict the test set data, because the model is quite complex. But in underfitted models, the model is so simple, it means that the model is not even able to predict the train set. Yeah.
I am the dumb child. So we have some kind of demonstration of what is overfitting and underfitting is. For example, this is the linear regression time for this data.
We have a set of data.
Yeah.
We want to fit a curve or a line on these sort of data. We start with a
Linear
polynomial regression with degree of 1.
Yeah. Then I'm sorry. We should run it again. All right. and we increase the degree of polynomials.
It gets better and better.
But at some point,
By increasing the degree of polynomial, the model, the regression model, starts to memorize the data, and it gets worse and worse.
so what it means is that it's going to be trained on the training set, but not going to give good answers, accurate answers in the test set. So we come back to the presentation. What about this? So let's go to the supervised and this is the oldest case.
Yeah. So, as we talk about supervised and unsupervised learning models, we have two different groups of supervised models, classification models and regression models, and also two sort of unsupervised models, clustering and association.
Yes, exactly.
Yeah. In regression models, we are trying to predict the continuous values, continuous figures, like for example, height of the people in this room, and we try to fit a regression model, a mathematical expression for predicting the, for example, height of the people in this room based on their weight, for example. And if there is a good correlation between them, you can see such a curve like this, or with a few, with less correlation, you can see something like this. Yeah.
And for the classification models, we don't have this continuous variable, so we have discrete values to predict. So we are doing some kind of classing. We are separating two classes from each other or multiple classes. So the classification model is going to work as, getting the output of the class by getting the features. So it is going to somehow predict the class of the data. And about the clustering, do you want to talk about that clustering?
Yeah. In clustering, we're trying to put the data into different classes without knowing the labels, without having the labels in the original data.
As I did before.
Yeah.
All right.
In the first and foremost, the simplest way of regression is linear regression. For example, if we have these numbers, 1,000, 1,200, what is the next number?
Anyone? Yeah, okay.
1,400.
It's very easy.
Yeah, it is quite easy because there is a quite linear relationship between the data. And in linear regression models, we have a linear expression, a mathematical expression. In this case, x is the independent variable that we have. Y is the dependent variable, which we are trying to predict. And also we have a b0, which is intercept, which means that at x equals 0, what is the amount of y, what is the amount of dependence variable, and also we have a b, which is the slope of the regression line. And also the other part, the last part, is an error, e. Error is the difference between the predicted value and the observed value. It's very important to evaluate and assess the performance of a regression model.
The name is scary. Error. So if we come to the very simple example, let's say we have an estimation, we want to have an estimation of how many people is going to attend to this event. And we have y as the number of attendants and x as the hours of advertising. So if we put in a linear regression, it should be something like this. So the x is going to be replaced by the hours, and y is going to be predicted value of number of attendants, for example. B0 and B, our coefficients need to come from the historical data, so maybe incoming years. So now we come to decision tree model, which I like it very much. I'm sorry, Milad, I'm not a mathematical guy like you. I like to go back to the oranges analysis. So mainly, let's say again, we have and I'm trying to ask some questions from myself And by that questions, I want to separate these. So the first question, for example, is the diameter larger or equal than 3? 3 is a value, let's say. So if it's false, I will put them in another bowl, and if it's yes, it's true, I will put them in another bowl. Later, I will ask another question, which says I'm including another feature to separate them. If the answer is false, and for example, if the color is orange, if it is true, I'll put it in another bowl, if it's the oranges. And if it's false, I'll put it in another bowl, which is going to be apples. Real-world applications of decision trees are something like a decision tree for heart disease, which you have the root node, which is started to separate the data. There's so many things to talk about this root node, which we don't have time in this 45, 60 minutes. So you have the age, you then come to the decision node, which you're asking some questions, and then you just include another feature to do the separation. And then you're doing another questioning, which leads you to the leaf nodes. Leaf nodes are something that we had our decisions in. And this one, and this, the other three, is one of the real examples that we prepared for the water pipe failures, which it is a very simple tree, it's a very weak tree. It says that if the pipe is main pipe, if the answer is yes, we're going to ask another question, adding another feature. Is the age less than 50 years? If it's yes, we will go and add another feature. Is the length larger than 200 meters? If it's yes, it is going to fail from the observations, from the data. And if it's no, it's not going to fail. So the leaf nodes are going to give us decisions. But what is the pros and cons? The positive part is it is computationally cheap to use. It's easy to understand. We have the ability to deal with the relevant features, but there's a negative part. So it is prone to overfit, because it's a very simple model. So it is very prone to overfit. It is poor generalization performance and low prediction accuracy. So what can we do? The idea of ensemble models come from here. So we are saying that, for example, if we're going to choose a leader for a group, we're doing some kind of voting. We're not just going for a simple decision tree or simple person for his decision. So we're doing some kind of voting, averaging the decisions. And this is why someone that time thought that if I could grow a tree, I can grow a jungle. So it is what the most famous thing come along, random forest. Random forest is, well, I'm not going to talk about this bagging and boosting things because you have to go, we have to talk about it so much in other sessions. But this session, we're going to talk about what is the ensemble model really means. It becomes some kind of averaging, doing some combining base learners or weak learners, and also doing some kind of voting in their decision. And the most popular one is random forest. As you can understand from the name, it is using so many decision trees. And at the end, it is having a decision from all the trees, averaging or voting. And it is making this tree models a bit robust. And, okay, artificial learners. I'm very jealous that you started with the mathematical equations. So I'm going to talk about this artificial neural network in a mathematical way. So when we talk about the artificial neural network, this is very famous, we are talking about neurons. So what is neuron? Neuron simply takes an input, applies a logic, and gives you an output. But it is very familiar. It's very familiar to us. It is some kind of function. So neuron is like a function. And if you're talking about the neural networks, we will talk about this. There are network of neurons. So we have network of functions. The function could be anything. It could be linear, could be nonlinear, and any type of functions. And we are trying to have some relationship between the inputs and outputs, inputs and the features. And later we are developing some kind of relationship between the functions and getting the outputs. ANN, neural networks, could be used in regression, classification, and clustering. But again, I'm so sorry to get back to the apples and oranges. So we are planning to use a neural network for fruit image recognition, let's say. It is a neuron. The first input is the color, second input is shape of the fruit, and the output is fruit name. And also one of the main words that you will hear about the artificial neural networks is weights. So if I come to the weight, I will go with the example. We're going to choose what is the output or what is the food by using the ANN. And these are what we had in data. For example, we have a shape weight for something like 2. I have the color weight of 4. I have the shape class, which is, if it is round, is 1. If it's not round, it's 0. I have the color, if it's red, it's 1. And if it's orange, it's 0. I calculate the weight, and the number is 6. But what is 6? I have some kind of classes before. So I said that if the output, my outputs are going to be in class 0 and class 1. There are some kind of rules for class 0 and class 1. My class 0 is going to give us the total weight. If it is less than 3, it is orange. So the 3 is our threshold. I had a threshold value as 3 to define these two classes. And if my total weight is larger than or equal to 3, it is apple. So my output is going to be apple in this case.
Yeah. What we exactly do in clustering, and K-means clustering is an example of the clustering. In this method, we choose the centers for each cluster, and then we put all of the data which are closer to the center in a group, in a cohort, and in this way we can. Could you
Yeah, I will do a demonstration of that. So, wish me luck. Let's say this is our data, and there are no classes in it, so we don't have any cluster.
Before starting,
Yeah.
we can have a judgment of the number of clusters needed for this data.
Okay.
The
What do you
optimal
think the
number.
optimum number of clusters for this data? Babak? 4. Thank you. Our optimization expert. Anyone else? 2. Good. Anyone?
3.
Ah, okay.
Just something in between.
Very good.
In between.
They say 5 then.
Yeah.
You know, this is the problem of K-means actually.
12.
Yes. Good, great. So this is the problem of the K-means cluster. This is one of the negative points of it. So you have to define the optimum number of clusters. So if I started from no cluster, which it is this one, it is only one cluster, and the cluster center is here, to 2 clusters, and go forward, 3 clusters, 4 clusters, your answer. 3 clusters, your answer.
I like it.
And then 5 clusters,
Later.
6 clusters, 7, 8, 9, 10, 11, 12, anything. So it is some kind that you cannot say that it is true or false, but you have to define it. I mean, as we can see from the data, these are similar in a similar place and with similar values. So you would think that, yeah, this should be a bit one cluster. But you have to define the optimum number of clusters. If you want to define it, well, that's all good. So I'm getting back to my presentation, and again, switch the screens. Okay.
Yeah. How to know?
Start. Yeah, I hate this spot, but you can go.
How to know the model is performing well? How to know machine learning model is performing well? If you have a regression model, if you have a regression kind of machine learning model, we are trying to find continuous values. So there are some metrics like correlation coefficient. There's a serendipity mathematical equation.
Yeah.
I hate this sort of equation. But yeah, there's some sort of presentations.
I will do some
Explanation.
kind of demonstration for that, but you have to tell me.
Yeah.
So
Let's start from 1. Yeah. If all of the predicted values are quite exactly equal to the observation values, it means that I have a very good ideal regression model. So in this case, the correlation coefficient is equal to 1. by getting far from the observation values. Yeah, you can see the correlation coefficient reduces at r equal to 0.
I will reach there. That's all.
Yeah. For example, like this, I can see that there is no meaningful correlation between what I have predicted and what I have observed. And by getting reduced more and getting negative values, there is an inverse correlation between the predicted values and the observed values. Yeah. At r equals to -1, I have an ideal indirect correlation. Yeah, indirect correlation between these two values.
So if I come back to it,
so in regression models, there are some other metrics like r squared, which is the square of r, or root mean squared error, or Nash-Sutcliffe error metrics, things like that.
and for the classification, no, it's not.
Yeah, click on it.
All right. For the classification models, which we are going to find the classes, different classes. And it is one of the famous things about this, defining the classification. I mean, evaluate the classification models, confusion metrics, which you're going to hear everywhere. By these values, by these 4 values, there are so many other metrics for the classification tasks. But what are the meanings? If the model is predicting the negative value as negative, which was actually negative, it is a true negatives. If the model is predicting the positive values and they were actually the positive value, the positive class, it will be the true positives. So if we sum them, it is going to be the true values that model predicts. And if the actual value is negative and model predicted that value as positive, it is going to be false positive, so it is an error. And vice versa. So the actual value is positive and model is predicting it as a negative, so it's going to be false negative. One of the famous things about this accuracy of the model is a formula like this. So you have the true values divided by all the positive values and all the negative values. So it gives you the accuracy of the model. As I said, there are so many other metrics about this classification: precision, recall, F1, specificity, yes. Matthews correlation coefficient, something like that. So you can go and read about them. But this is the main thing. The confusion matrix is some very famous type of evaluating.
Count the number of the times that the model predicted correctly, truly, and the number of false predictions.
So it is not moving. Right? So the machine error. This is some kind of discussion. I was thinking that what will happen next? We asked this question. And I was thinking always that if someone's going to ask me someday that, is the AI or machine learning going to lead us to the end of the world? I don't have any comment. I don't know. I know that is very soon to talk about it, or maybe very late to talk about it, I don't know. With the ChatGPT, with everything that Babak told in his presentation. Really, I don't know the future about it. But I know that there's a long way to go.
And we had a nice discussion in between these 2 sessions about the future of AI, machine learning, and how we can rely on them, how we can work with them. Are they cheat GPT, chat GPT? We have to think about them twice.
But one other thing is to ask me that it is going to destroy our jobs. Yes. So do you, or can you say, who was the first person, who was the first character, lost his job because of AI?
Any idea?
Any idea, anyone? Anyone who lost his job or her job?
AI or any kind of an automation?
Because of any kind of computational intelligence or artificial intelligence.
Online copywriters.
All right.
Content
And before
creators.
that?
Before that, the first person, the first character.
Calculator.
Ah, calculator. I'm using them. I'm still using them.
Maybe it was a job at some point, you know.
Oh,
You
yeah.
go to someone, you say, can you please do 7 times 6?
Someone is sitting there getting
Yeah.
money to say that.
Well,
Oh,
just
7
like,
times 6.
just like there was the writer, you know, like because people didn't know how to read and write, so they would go to the writer and. But
Yeah, could
with
be.
the invention of typewriting, etc., eventually,
Yes.
and education.
Anyone?
I can think of many. The one I most hate is that you cannot call anyone talking to a person and you're just talking to a bot. It's personal anger.
Personal anger, yeah. The first character, I don't recall, is someone else, which is very famous.
Laughing Tom. Then watch this. Okay, if I laugh now, Tom. That's how it is, Tom. Progress, the machine age, and stuff like that.
Thank you very much.
Yeah.
Laugh.
Thank you very much.
Thank you.
Okay, we're looking for questions. Go on.
Can you please go to the slide that you had about outliers? By the way, this is not rehearsed. Can you do it, please do
About the
it? Outliers?
outlays. Think about your future.
I think it was earlier on.
The very beginning, actually.
Here,
Here's my-
here.
All right.
Yeah, there you go. So I think at some point we had this sort of discussion. I don't necessarily, I'm one of those who don't necessarily believe the idea of labeling something as outlier. Because yes, it is easy to say, okay, this data was perhaps wrongfully collected, or the patterns is not fit with what we have. But say, assume that we have another dimension. So I say something.
Say, yeah. A z-axis.
Yeah, that's the one. Say we have another dimension that is directly, right? Everything else within that direction, these 2 points are in that dimension, right?
Yeah.
So that other dimension, additional dimension, will solve the whole problem. We know that if there is a value to that, it's going to give you, it's going to collect this data, and it's going to predict this value. Otherwise, you're going to. My point is, how do we know that this is an outlier, or this is something that we haven't accounted for? Another measure that we should have measured, we should have tested, should have collected.
Right.
Where is the line? Where can we say that this is like this, or it's simply that we're missing some data?
I can give you a very simple example of what I did in the laboratory. I knew that, for example, the strain measurement for the PVC pipe is not going to be more than this value. If I got that value from the strain gauge, for example, or a sensor, I will say that, no, this is not true. It is not possible. So it is some kind of failure in my sensor or some kind of failure in my strain gauge. In this case, I can put my domain expertise and say that this is not acceptable, so it is an outlier. But as what you asked is, yeah, maybe in some cases I cannot say 100% that this is outlier or not. Even in some of the evaluation metrics also, that I disagree with some of the evaluation metrics for the machine learnings. Because I think that data is not only a value, it's not only a point, it is money. So maybe in some cases I can say what is outlier when I have the domain expertise about that data. But if not, we should think twice before removing it, before doing any processing on the outliers. And it is a really hot topic these days. So the outliers and missing data are hot topics because we have this data scarcity in industry. So it is a very hot topic. I would appreciate to talk more about it later on. Any other questions?
I mean, related to that, I do believe there is, if you talk about outliers, because you're implicitly saying that there should be a trend to follow, and this outlier didn't follow. Yes. But it comes to me this old joke where, you know, there's a guy driving on the motorway, and on the radio there's, oh, pay attention in the motorway, there's one crazy people driving in the wrong carriage. I say, one?
Yes.
You know, and so what if basically the blue ones are the outlier, because the phenomenon we are trying to replicate or to investigate or to measure is not be measured by your strain gauges or your system or whatever it is. So when you say outliers, you implicitly say they are lying outside my model. Maybe your model which is lying outside the actual response.
Yeah.
Right. So, and of course, in this case, good common good sense would say yes, they are too far away from the thing. But if you add another 1,000 points, are those being completely out of the picture?
So this is something that you have to think twice. So it is another case which now, if I have so many observations which are showing something else from the trend, I should think twice. I should look after something else to see that what is the reason, or is there really something that they are somewhere else? What is the problem, or is problem? I mean, am I the problem? I will look forward to ask so many questions because we are researchers, so we have to ask questions to verify that these data are all right or not all right. But again, it is not a binary thing, so it's a fuzzy. We cannot 100% say that this is outlier or 100% say that it's not. So, in my own case. Yeah.
In such cases, I'm trying to act like a detective.
Okay.
Have a list of suspects, for example, if in the lab case you talk about. For example, if I have some measurements which are quite far from my expectations, I'm trying to have a list of the suspect factors. For example, I can think about whether the temperature has increased in that day of measurement unexpectedly, if something else has changed, if these are my suspected factors, and I'm trying to test them. Has some of them changed? Is it going to be the reason behind these unexpected values or things like that? And in all of the cases, I'm still relying on my expertise, on my domain expertise.
So regression, classification, clustering. Are there other methods that we maybe don't have algorithms for that would be, because you asked what's the future.
Okay. Good. This is good.
So I'm thinking, what other methods could we come up with that maybe we don't have algorithms for yet?
We have to talk, first we have to talk about the need. What do we need?
Yes.
First we have to think about the needs and then about the algorithms. What do we need? What sort of data you have and what sort of predictions you want to do. Then we can think about the algorithms to solve the problem. For example, sometimes you have just categorical data.
Yeah.
So you need some other sort of algorithms and models to predict. Or you have numbers, but you want to predict the categorical values or categorical features. And in all of those cases, you can think about new algorithms, new methods.
Yeah.
But what's the need here? We have to think about the need.
So do you have any ideas in mind of what it's going to be?
No, I don't. I'm just thinking like quantum physics. Is a bit different. Like you can't really predict because it can be multiple places at the same time. So
Yeah.
Stochastic,
fuzzy logic.
fuzzy.
So maybe there is some method around that topic would be interesting in the future. That's not a clear idea.
My own thought is about the optimization and about the machine learning. There are so many algorithms, very good ones, very, very good ones. And maybe there is no need to develop new algorithms. We should find the use case. I mean, for example, when you're looking at some of the use cases as, for example, the heart attack or, I don't know, pipe failure prediction, anything else, I mean, any use case, any data set, we should try to use the best algorithm for that. And also we should try to teach or make that algorithm learn well by the data. In new academic trend, when you look at the papers, they're always looking for the novelty in the algorithm itself, but no, it is not needed really. Should look for the additive, let's say, methodology to teach that algorithm well. So it is my own idea, but if it is going to be need for another algorithm, there will be some. Good question.
I didn't have really heard the question, but I think like this outlier problem and other things just highlights the fact that our main bottleneck is not the algorithm itself, but the entire pipeline. So if you have any sort of data, you will have outliers. Even detection of outlier can be a machine learning application of other algorithms to detect what outlier is. But then that may not work because domain knowledge may not be actually involved into that machine learning algorithm. And so many algorithms exist, we probably will find it hard to actually go through all of them, find what is the best case for us, and then choose such a pipeline which will actually encompass the actual model here. Because say specifically for say as complex things as research, we are not going to mostly work with linear models for most of our work cases. We may even not be aware of which degree of polynomials we fit our models. Are we overfitting? Are we underfitting? So it's one of those cases where it's much harder to just go and just apply something. We can start doing basic regressions to start piecewise fitting and moving forward, but I guess that's the main bottleneck. I guess the question in that would be, where do you see, like how much do you see picking up? I mean, today, the most amount of enthusiasm has been generated by ChatGPT, where it is like very specific NLP. The NLP field has exploded in the last 10 years or so. So there have been very specific algorithms and things made there. But in all of the quantitative field, optimization has existed forever. It's just being put up together in a pipeline to let it work to it. So how do you see it actually picking up more, or is it just going to be limited to NLP?
You want to answer this one?
No. I think, according to my experience in the industry, the main bottleneck in not all of the branches of science and technology, but in the branches that I have been involved so far, is about the data. Pure data, clean data, reliable data, updated data. We in some parts of engineering and science technology, we are still running low on data, enough data to train our models, train reliable models, and we are still needing some sort of sensors and any sort of sensors to gather data, to store data, transmit them to our clouds, and store them for training our models, things like that. According to my experience, the bottleneck is about data.
Data.
We have a lot of algorithms.
I just have one comment, then probably want to bring it to a closure, is that all these methods and systems try to find order where order may not be there. So if you see something like that, you say, well, it's kind of intuitive where it's going. And as you said, my understanding of the domain may guide me in what is there, which is probably not very useful, applying machine learning or artificial intelligence if I already know what I'm expecting. I believe that when data sets are much more dispersed and much more vast and much more complex, that you want to help the support. And in medical science is a typical example. I mean, you will have a system that, it's relatively simple to say, if you're a smoker, if you have like a very sedentary life, you are eating bad, you are very all these kind of things, and you have familiarity, where you will develop this sort of disease. It's less clear explaining why healthy non-smoker young people have the same disease. And there's no sort of correlation. Is pretty much, we are substituting in a way the future tellers with the machine learning. So, all what we can say on relatively simple data sets that relies on our degree of expertise is something. When we step outside and we go to trying to find the order into the disorder, this is where we are putting a lot of faith into the machine learning, which is, I don't know how much this is well said.
I agree with that. And Bobak, you want to add something?
Just
My own thought, as you said, data which you are feeding that machine learning model or any AI model is the most important part. And when you have reliable data, as Milad said, it means that the accuracy, or let's say the trend of that machine learning, is going to be near to reality, or in some cases. But if not, it is going to be some kind of random generating things which a fortune teller would do. And from those randoms, maybe you hit the target twice, but it is overally not the answer to the question. So I definitely agree with that. Thank you very much again. And we will have a relay. How can we start sharing?
Just
Okay.
like that.
Really?
Red button.
Oh, yes.
Thank you.
Great.
Nice.
All right. So thank you very much one more time to Ramiz, Milad, Babak for this very interesting. I think we were able to explore to a certain degree what is behind the applications, what is behind the algorithm. Although I truly appreciate you haven't been on the rabbit hole or showing very complex coding and things, because you would have lost me very long. So I think it was very interesting and open. Give the interest, tune the interest that is now the hype which is around these topics and implications. There may be scientific implications, of course, but also kind of legal implications. Who is responsible for what a artificial intelligence system is suggesting? Moral implication, what is wrong, what is good. So yeah, I think it's a very timely discussion to have, and I truly appreciate the way you walk us through the whole thing. So one more time, thank you again, guys. Well done. And so thank you very much for the audience, the online audience, and the people here. For the people here, there's a bonus, which is some catering outside. Unfortunately, our liners are not going to enjoy that, but we can tell you that I think that you get the most of the morning in this very informative and interesting session. So thank you.
Thank you.
By the way, if you want, we can take a picture of you.
Do you want to get the main PowerPoint up, and then that would look like it.
Thank you.